Okay, so we'll go ahead and get started. I want to start with this one. If you remember, we ended talking about the Ka expression. So this is for an acid reacting in water to form hydronium ion, H3O plus, and whatever the conjugate base is. Okay, and then we can write the Ka expression. So I just want to get us started by having you guys write. Why don't you write the reaction itself and the Ka expression? So, reaction in water and then the Ka expression. So basically just like the slide above, but for these two specific acids. So if you're not remembering this, whatever, look at the first one that I'm writing up here and then try to do it on your own for the second one. Kind of copy the form. All right, just one more minute to check your work and get caught up to where we're at. Okay, so a couple important things we can use as like a review for what we were doing on Friday. The first one is obviously, what do we mean by an acid? So the acid is donating its H+. So it's going to form H3O+. The water, when it accepts that proton, is going to form H3O+. And then the thing the acid turns into should be one less hydrogen, and the charge should have gone down 1 unit because it left behind its electrons. Okay? So we can also label them, like this is our acid, and the thing it turns into is called the conjugate base. Because remember, the reason why we call it that is because in the reverse direction, the ClO2 minus would be acting as a base. It would be accepting the H plus in this case. So like, let's just show that when the HClO2 reacts with water, the hydrogen goes to H2O. So the HClO2 is the acid. In this case, the water is acting as the base because it's accepting the H plus. Okay, so it turns into H3O plus, or the conjugate acid, and HClO2 turns into ClO2 minus, the conjugate base. But if you think about it in the reverse direction, now H3O plus would be giving the H plus to ClO2 minus. That's why we call it an acid on the far side and a base, because in the reverse direction, that's how they're behaving. Okay? And then we consider those pairs, like the red ones are a pair, the green ones are a pair, because they're only differing by an H plus. Then when we go to write the K expression, we call this a Ka because it's a very standard reaction. Like it's always the acid with water forming H3O plus and the conjugate base. So it's not any acid doing anything and has a K value. It's specifically reacting in water, donating its proton. And so you'll get tables, we'll see this down here. You get tables where it gives you the formula of the acid and then it says the Ka. So it doesn't have to tell you the reaction because it's every single one of these is reacting with water, forming H3O plus and the conjugate base. Okay? So it's not, when it says Ka, it's not going to tell you the reaction. You just need to know what reaction that corresponds to, which is why we practiced by writing these ones. Okay? So then the K for that is products over reactants, which means this is going to look the same every single time. It's going to be H3O plus, the conjugate base, and the original acid. The other thing that you should take notice of, and is a good reminder, is the fact that the top one, I wrote a double arrow, and the bottom, I wrote a single one. We're getting to the point where you guys should be able to know when you should do double versus single. So if you remember, these are our 6 strong acids. So if it's one of those, HNO3 was the second one on our list today, that means it goes all the way to products. There's not going to be any HNO3 left over. It's all going to get converted to H3O plus and NO3 minus. So that's when we write the single arrow. Not even just product favored, but only products. And then the weak acids are anything else. Any other acid that's not one of those 6. So HClO2 in this case. And so that would be a double arrow, meaning there is a balance point. It's actually reactant favored. And so we need to indicate that by showing the double arrow, that there is an equilibrium that's, not all the way to products. Okay? Okay, so the next thing we're going to do is take this HClO2 and we're going to do an ice table. So it's 2 slides down from here, and it says you have a 0.75 molar HClO2. what's the H3O plus concentration, okay? So make sure you have, this K expression. You're going to pull that down and use it again to calculate the H3O plus. Okay, so that's this question here. Now there is a concept question. You can think through that first, or you can do the calculation and then think through why it is what you get. And then you'll also need this K, HClO2, okay? So that's the Ka, the actual value, 1.1 times 10 to the negative second. And you're going to do an ice table to figure out the H3O plus. So this is the point where if you're like, oh, we're going to keep doing those ice tables, yes. So if you did not feel confident enough after the last test, this is the point when you want to really dig in and make sure you're confident with those. They're a little bit simpler because they're all coefficients of 1. The only time we ever see non-1 coefficients is when we have a hydroxide where there's 2 of them. Otherwise, it's always a coefficient of 1. So it makes them a little bit easier. Now this one, you do still have to do the quadratic because the K is only 10 to the negative second. So it doesn't necessarily get rid of that, but it does simplify things a little bit. So if you at least get to this part, like obviously I want you to know how to solve this, but if you haven't done that, you know, in class time, that's okay. But just make sure that you've got everything set up to the K. So that's equal to x squared over 0.75 minus x, okay? So we get that x is equal to 0.0855 molar, and this is the concentration of the H3O plus. It's other things too, right? The concentration of the ClO2 minus. But when we're talking about acids and bases for that matter, what we really care about is H3O plus. Because when we say something, when we say an acid is corrosive, we don't mean the original acid. We don't mean the HClO2. We mean the fact that it turns into hydronium ion. So the hydronium ion, the H3O plus, is what causes acidic behavior. So when we're looking at all of these problems, you know, through the rest of the year, we really care about H3O plus. And that's 9 times out of 10, that's going to be what the question is asking for, either in this form or in pH, which most of you are familiar with, I think, from biology classes or environmental science or whatever it is that you're currently studying. pH is, you know, a very prevalently discussed form of how we measure acidity. Okay? All right, so we found out that this is 0.085 molar H3O plus. The concept question said, at equilibrium, will the H3O plus concentration be 0.75 or less than that? Well, it's definitely less than that. It's significantly less, right? That's because this is a weak acid. So you had the reactants and products and it went like this, right? Little bit of products was made because it's not a tiny K, but it's 0.011, right? So it's still quite reactant favored. So you did not produce a whole lot of product. And you know that anytime it's weak, it's not going to produce all of that. Now let's juxtapose this with nitric acid, which was the other one we wrote the equation for. So nitric acid is a strong acid. So we wouldn't ever write an ICE table, and I'll show you why, but I'm going to show you like what it would look like. You don't actually think of it as being minus X when it's a really big K. When it's a strong acid, you say all of that HNO3 is going to get used up. So you say minus 0.75 and there's 0 of it left over. Which means that on the product side, it's adding 0.75 and making 0.75 of the hydronium ion. So that's when the concentrations would be equal. When you have a strong acid, all of it gets converted and makes that same amount of H3O plus. So 0.75 nitric acid is going to be hugely more corrosive than 0.75 molar HClO2 because so much more of it gets converted to the H3O plus. Okay, so this is a key point. You do not do an ICE table for strong acids. You just know whatever the molarity of the strong acid is, all of that gets converted to H3O plus. You don't need to do a calculation. You don't need to do an ICE table. But for a weak acid, yeah, you're definitely going to have to. Okay, so the rest of today, we're going to talk about how do we use these the H3O plus number, the hydronium ion concentration, and how does it relate to other quantities in this water solution, and how do we report that? So by that, I mean H3O plus is going to be inherently related to hydroxide ion, OH minus, and we are going to use both pH to report that, as well as something you've probably never heard of, which is POH, that really is not all that useful, but we use it to kind of make calculations easier. Okay, so that's going to be the rest of today, and then we'll get back to actually using acids and ice tables and how they relate to each other on Wednesday and Friday for that matter. Okay, all right, so I skip over the overview because that's like for you to refer back to as a summary of today. But to start, we need to talk first about another relationship, really it's like an acid-base relationship that's constantly going on in water, even in neutral plain water, but it's only going on to a very, very small amount. In fact, I'll just scroll down and show you on the next slide. There is a K associated with this reaction, and it's 10 to the negative 14th. So it is a teeny tiny influence. It's only ever so slightly ever so slightly product made, very, very reactant favored, okay? And this is water reacting with itself in an acid-base reaction. So one little molecule of water and one molecule of water, they swap a proton. One proton goes from one water to the other, and it makes H3O plus and OH minus. So just like that. Which may seem weird, but it is so few of the water molecules that it's just not really noticeable. When this is in pure water, the amount of H3O plus and OH minus are equal to each other. So this relationship down here is the K for this reaction, because K is equal to products over reactants, but pure liquids aren't included, so the water's not included. So we can actually relate H3O plus and OH minus to each other. So let's pretend we had an ice table. Not pretend we have an ice table, but pretend we're going to calculate this amount. It doesn't actually matter what we start with, because we don't include pure water. We would just look at the products and say some of each of these is getting produced. Okay, so it's some amount x squared, H3O plus and OH minus. Let me write it as symbol form first. So x times x, or x squared, is equal to 1 times 10 to the negative 14th. So if we take the square root of that, we find x is equal to 1 times 10 to the negative 7th, meaning H3O plus is equal to OH minus, and they're both equal to 1 times 10 to the negative 7th. So in any water solution, if it's just water, pure water, those two concentrations exist. It's such a small amount, we don't ever really notice it. Also, they kind of have a tendency to cancel each other out. So even in pure water, you're not going to really notice any of those properties that they exhibit. Okay? Why do we care about this? Because usually we're talking about this not in pure water. We're talking about adding some other acid into it, like the HClO2 that we did earlier. Right? So when we put HClO2 into water, this is still going on, this reaction of water forming H3O plus and OH minus. But by adding the HClO2, we increased the H3O plus, right? It started out as 1 times 10 to the negative second, and we calculated it to be 0.0855, okay? So by adding the HClO2, we increase this to 0.0855 molar, even though it started as 1 times 10 to the negative 7 when it was neutral water. Okay, so Le Chatelier's principle stands here. If I increase the H3O plus, the reaction's going to go this way, meaning the OH minus will go down. So this relationship means that if one goes up, the other one has to go down. So I want you to use that value, the 0.0855, and tell me what is the OH minus now if the H3O plus is 0.0855. We know it went down. It's got to be less than 1 times 10 to the negative 7 because the product of the two always has to be 1 times 10 to the negative 14. So do that math and figure out the OH minus concentration. All right, so I get that OH minus is 1.17 times 10 to the negative 13th. So significant drop. Neutral water, they both were 1 times 10 to the negative 7. Then we added the acid. This one went up to 0.0855, and this one went down to 1.17 times 10 to the negative 13th. So the big takeaway here is if you know one, you can calculate the other, and they will always be inverse of each other. In neutral water, they're the same, and if they change, it'll make the other one, if one goes up, it'll make the other one go down. Okay, so that's one important relationship that we need to maintain as we're going through this. So take just like 2 or 3 minutes. Make sure you're comfortable plugging these into your calculator to find out the other one. I would say be careful, like put parentheses when because this is going to be, to find the OH minus here, you're going to be doing 1 times 10 to the negative 14th divided by 4.3 times 10 to the negative 3rd. Just be careful, unless you know you don't need them because you're using a special exponent key, be sure to put parentheses around that, or else you would be dividing by 4.3 and then multiplying by 10 to the negative 3rd instead of dividing by that whole quantity. Okay, so take just a couple minutes and solve out each of these for the other one. Hopefully you're seeing a trend here with the ones where the coefficient is 1.
Sorry, is that negative to the 14th, that bottom one?
Yeah, so that's me calculating it.
Yeah.
That's not the answer. That's the answer, but yes,
Yeah.
that's the calculation.
Okay.
Because that's the relationship up there is the one that's typed H3O plus times OH minus equals 1 times 10 to the negative 14. So hopefully you saw pretty quickly those top 4. When you have the coefficient of 1, the exponents just have to add up to the 14. So it gives you a really pretty clear sense of where things are at. Just like when it was neutral, it was 1 times 10 to the negative 7th. It was 2 7s. They add up to 14. So like here, negative 11, that's going to be 1 times 10 to the negative 3rd. Okay, they have to add up to 14. Okay, so this is the first important relationship. Next, we need to talk about pH, because that's usually how we're going to report how acidic a solution is. So if you guys remember, I'm going to scroll down a bit to a pH scale. Okay, just look at the top one here. So if you remember from, I don't know, any other biology, chemistry, whatever classes, 7 is neutral. Anything less than 7 is acidic, and anything more than 7 is basic. And this scale is used pretty much because before there were calculators, at least handheld ones, it was very annoying to work in exponents. So, having concentrations 10 to the negative 3rd or 5th or whatever was obnoxious because you had to use the slide rule. So they used logs, which basically undoes exponents, to put it in a easier form to work in. Okay, so going back up to that next slide here, when you see P, it means take the negative log. So pH is technically H3O plus. Sometimes people will abbreviate H3O plus as H plus because it's like you donated the proton but not to water. You just kind of left it hanging out there. I like calling it H3O plus because that's what it really does, is attaches to a water. So pH means take the negative log of the H3O plus. Okay, we'll do other P's, which is POH, take the negative log of the OH minus, or even pKa, which is take the negative log of the Ka. It's just to help get things out of exponent form. Logs are kind of like multiplication division as far as logs and exponents. So if you have something that's like 10 to the 3rd, the log of that would be equal to 3. So log 10 to the 3rd is equal to 3. So it kind of undoes the exponent. So let's do a couple of these. I want to start with that value we used before when we were doing HClO3. So this one, 0.0855. Okay, so I'm going to take the negative log of that to give me the pH of this solution. So I'm going to do it up here so that you guys can see how I'm punching it in my calculator. Okay, so on mine, I just put negative, and I have to say 1. Most calculators, you don't have to put a 1. You just can say negative and hit the log button. Mine makes me do a 1. Then I hit the log button. Also, most calculators just say LOG. They don't say 10. It's log base 10 versus natural log. Why is it not on here? Oh, right there. LN, which is log base E, the constant E. So we're using log base 10. So negative log of 0.0855. So 1.07 is the pH of that solution. So punch it in on your calculator. You're going to do a couple in a second, but 1.07 for the pH of this solution. This is that original problem we were doing with the HClO2. Now, POH is way less common. It's probably not something you guys have heard of before. It pretty much just makes calculations a little bit easier sometimes. We don't actually report things as POH usually. But let's do that for this one too. We have the OH minus. Let's take the negative log of the OH minus and determine the POH. So I'm going to do the same thing, but now for the OH minus. So negative log of, what was it? 1.17 times 10 to the negative 13th. Okay, so the POH is 12.93. Okay, so POH, this is for the same solution, 12.93. Okay, maybe you've seen it already, maybe not. These two things add up to 14. So just like H3O plus and OH minus, when they're multiplied, equal 1 times 10 to the negative 14. pH plus POH equals 14. Okay, so that's another important relationship. Don't worry, I have a summary page with this. So we've done pH, POH, and now we're creating this new relationship here. Yeah.
So what did you plug in for pH and POH?
Negative log, so it's right here, negative log of the H3O plus. So for the one we did before, it was 0.0855. And then negative log of the OH minus, which was 1.17 times 10 to the negative 13th. It was from that previous problem. We'll do others down here too.
I see. So the 0.855 was the H3O.
Yes, the H3O plus from the HClO2 acid. Yeah. Okay, so I want to preview my little summary page, and then I'll have you guys work these ones. So it looks intimidating to start. It's very helpful. This is it's not in the book. This was me, because I think making these relationships all clear is useful. So to convert between H3O plus and OH minus, you use that equation. H3O plus times OH minus is 1 times 10 to the negative 14. So we've talked about that one already. To get from the H3O plus to pH, don't ask me why that guy's on the wrong line. We use the negative log of the H3O plus. To get from the OH minus to the POH, we use negative log of the OH minus. And then to get between pH and POH, we use adding them together equals 14. So we've done all of those equations so far. There's only 2 left. So the 2 that are left is how to undo the log, which, like I said, log and 10 to the something, those are kind of inverse of each other. So the way you undo pH and get back to H3O plus, maybe I'll rewrite this on the other side so you realize that that's this direction, this arrow. 10 to the negative pH will give you H3O plus. Okay, and then same for the other side, 10 to the negative POH will give you OH minus. So they're 2 different equations going back and forth, because you can't just you can't divide by a log. It doesn't work that way. The way you undo a log is by doing 10 raised to that value. Okay, so let's do this first set of practice problems, and then we'll probably leave the last one till Wednesday. So using these relationships here, I want you to work through these problems. We're going to do the first two together. Determine the pH of each of the following solutions. Okay, so for the first one, we just take the negative log of the H3O plus. That's going to give me the pH. So the negative log of 1 times 10 to the negative 6th. This is how logs work. That's equal to 6. So if your coefficient is 1, it's just that number. I don't care if you plug it in every time. It's just good. This helps you understand what logs do. And then for the OH minus 1, over on the other side, it says determine the POH and the pH. Okay? So POH is negative log of 1 times 10 to the negative 3rd, or 3. And we know pH plus POH equals 14. So POH should be equal to 11. Sorry, pH should be equal to 11. Okay, so do those other 4, following kind of the same general format. Make sure you're comfortable with these. And then we'll check answers and probably stop there. Okay, so my recommendation, because you do, since I told you about these equations, the other two that we didn't do yet, you could do these problems down here. They're just like multi-step ones. So you could try those, or maybe even better is start in on the homework. Don't like beat yourself up if you're not getting it, quickly, because we haven't like practiced it all. But getting a start on it will make the material on Wednesday feel a little bit more comfortable. So let me scroll up there, Colton. Okay. So just get a start on the homework, practice a couple of these, make sure you're feeling comfortable with kind of these back and forth calculations. And use that flow chart thing, this one. Okay? That's it. I'm done. Yeah.